So we're going to look at graphs of linear relations and what they specifically look like. We kind of looked at this stuff with some of our previous when we were looking at linear lines of best fit and things like that. So some definitions. A relation is a pattern between two variables. In general, we use x and y. But if not, x and y, it could be distance and time, or it could be cost and liters and cost, or kilograms and cost. So any two values that are related to each other. But again, our general format would be x and y. There's different ways of expressing the relationship. And we just pick the one that makes most sense to the situation, or possibly one or two, depending on how we're trying to illustrate the data and who we're trying to illustrate it to, if we're trying to highlight some of it. So one way to illustrate a relationship between data is to write out ordered pairs. 2, 3, 3, 5, 4, 7. Again, these are written in the form of x and y in that order. We could put them in a table, and we call that a table of values, or sometimes a T-chart. Students use the term T-chart because it kind of looks like a T. So x and y, we always start with the dependent column, or the independent and then dependent x, y values. And you'll see these 2, 3, 3, 5, 4, 7. There's our 0.23, there's our 0.35, there's our 0.47. We can graph them. And so there's our table, or our ordered pairs, and I've graphed them. So 2, 3. 2 on the x-axis, 3 on the y-axis. 3, 4. Or 3, 5. Fits there. 4, 7. Fits there. And then I've even connected the dots to show that this is a linear graph, because it is represented by an equation as well. 2x minus y equals 2x minus 1. So if we look at that, 2x minus 1. So we take the value 2. 2 times 2 is 4, minus 1 is 3. 2, 3. 2x minus 1, we have the next x value is 3. 2 times 3 is 6, minus 1 is 5. 2 times 4 is 8, minus 1 is 7. So that's how the equation works and matches up to our table. And then we can state it verbally as well. It's 1 less than twice a number. So this is twice a number, and this is 1 less than it. Now, when we're working with tables of values and graphs, we can take our information and create a table, and then use that table to help us graph. In most cases, we like to get about 5 or 6 points when we're starting out, just to get some practice with graphing. Later on, you might reduce that number, but when you get into some other types of graphs, you may need to use more points because, 1 or 2 points are good enough for a linear relation. When you get to quadratic or cubic relations, you're going to need more points to actually see the path that the line will follow. But we're going to do a few here. So we got a pizza shop selling large pizza for $10 plus $3 per topping. We want to create a table of values to show the price for up to 5 toppings. So we got 0. So this is the number of toppings. So the number on top, and this is going to be the price. So we got 0 toppings, 1, 2, 3, 4, and 5. And then it's $10 for the pizza plus $3 per topping. So no toppings, pay $10. 1 topping, you're going to pay an extra 3, so plus 3. Then plus 3, plus 3, plus 3, plus 3. So just keep adding $3 each time for each additional topping. And now we can take those points, we can plot them on our graph here. We got 0 and 10. And do note on my graph, I go 0 to 10 and then I go up by 2s. So when we do that, what we can do is we put this little kind of Z through the line, and that tells us that it's a broken graph and that we're skipping some points because there is just going to be a big gap at the bottom otherwise, and we don't want to waste some space. So we've skipped those points, and so we're starting at 10 here. And so we got 0, 10, 1 and 13, be about here in the middle, 2 and 16, 3 and 19, again, about in the middle here. We're trying to be as accurate as we can. And just to note, when I drew these graphs, what I did was I took a second piece of paper that had the same, because the lines are the same width apart, I can turn it this way to draw my lines, and then I can get a nice pretty graph. I drew a set of dots down here and a set of dots at the top, and that allowed me to make a nice pretty graph. Continuing on, we have 4 and 19. What do we have? Oh, I made a mistake on there, didn't I? 1 and 13. No, 2 and 16. 3 and 19, sorry, 4 and 22. 4 and 20, I was doing it right. 4 and 22, and then 5 and 25. So I can plot out all my points, and I've now graphed the relation. So is this graph linear? So this is a linear type of relation. They all fit and move in a pretty straight line. Okay, so they all fit in a straight line, and this graph would be linear. And is it increasing or decreasing? Well, going from left to right, as we increase the toppings, the price increases. So this is an increasing linear relation. Now, I didn't connect the dots, and I want to make a note of that. I didn't connect the dots in this case because it doesn't make sense to. When you're buying toppings, you're not likely to have 0.5 toppings. Or if you do, you cover half the pizza. What if you cover? Well, you're not likely to have 0.01 toppings. You might not have 0.01 toppings, so having a little point right here doesn't make any sense. The pizza places would not likely sell that way, so it makes more sense to say you either have 1, 2, 3, 4, or 5 toppings versus in between. So I didn't connect the dots because there's no values that actually fit in between here. You're not going to be spending $12 on toppings or on a pizza at this place. So what is the cost of an 8-topping pizza is the next question. And so if we take a look at that, what we can do is we can actually make ourselves an equation to represent this. So the cost, we use C for cost, equals $10 plus $3 per topping. So it's $10 plus $3 times the number of toppings. We can check if that works by putting in the values from our table. If we put in a 1 there for toppings, 3 times 1 is 3. 10 plus 3 is 13. And that matches up. We can try another point. Let's try 4. 3 times 4 is 12. 10 plus 12 is 22. That matches. So that's good. So our formula is working here. So the cost for an 8-topping pizza is going to be 10 plus 24, or the cost is going to be $34. So we can take that data and information and we can use it to make ourselves an equation. Looking at some tables, trying to understand them next. For reading tables, you can identify a table as a linear relationship if there's a constant change in the x column that produces a constant change in the y column. So when I say constant change, I mean it's going up by the same amount each time. So if we look here, 6, 7, 8, 9, it's going up. These are all plus 1, plus 1, plus 1 each time. And these are going up plus 1, plus 1, plus 1. Those are constant changes, so this would be a linear relationship. In this case, we see the same thing, plus 1, plus 1, plus 1. But here we see plus 3, plus 5 plus 7. This is not linear. So it's a non-linear relationship. Here we see plus 1 plus 1 plus 1. Here we see minus 100, minus 100, minus 100. While it's negative, it's still constant, so that is linear. Here we see plus 1 plus 2 plus 1. So that doesn't seem like it's going to be linear, because here it's plus 250, plus 250, plus 250. We would think the plus 2 would go up twice as much and should go up by 500. So this here wouldn't be linear. That would be nonlinear. So again, you're looking at linear relationships going up constantly in both the X column and the Y column, the independent and dependent columns. You can represent them using ordered pairs, tables of values, graphs, equations, or state them as well. And then we can use our ordered pairs to create graphs. We can use those bits of information there to create ourselves equations and solve for missing values. So that should get you started with some linear relations.